So as we mentioned before, we get our SL problem setup, definition is checked. We can get the eigenvalue and the infinity eigenvectors. Then if we have a smooth function which satisfies for the boundary conditions, then we can use the generated eigenvectors or eigenfunctions to represent this smooth function, right? So if we have fx, which is a continuous smooth function, which is in between the boundary conditions, which is the interest area. For example, x is belong to a to b. For our example, should be from 0 to L. Then we can use a linear combination of the eigenfunctions to represent fx. Okay. For example, my fx will be written as a linear combination. So sum from n equals to 1 to infinity Cn yn x, where this yn x is our eigenvectors associated with each eigenvalues should be infinity from 1 to infinity. The Cn is the coefficient we need to get the linear combination, right? So it's inner product of Fyn over Yn, which is a normalized factor. So this is only for normalization. If my Yn is not a unit vector. And the Cn can also write as, since we are interested in between a to b, so it's a to b, fx, yn, x, omega x, which is the weighting function, divided by, this is integral based on x, and divided by a to b, yn, x. Since this is orthogonal function, so yn inner product will be yn magnitude squared omega x on the weight function dx. And this is called generalized Fourier transform with respect to the orthogonal basis set, which is our Ynx, and weighting function omega x. Okay, so we have our continuous function, which is fx, is in the range of our boundary condition and satisfy our boundary condition in between a to b. And since this is a continuous smooth function into the a to b area, we can use our generated eigenvectors to represent our smooth function, where that the linear combination, the linear part, which is the coefficient part, can be gotten from the inner product of the Fyn over the normalization vector. If Yn is now a unit vector, so you can use the normalization part. And this is called generalized Fourier series respect to the orthogonal basis set Yn and the weighting function omega x. And we will make several examples, probably 2 examples regarding the fx, how we can use our already generated eigenvalues to represent our continuous smooth function.